Section 5.1, example 5, using squeeze theorem. So use the squeeze theorem to find the limit of each of the following sequences. Squeeze theorem just tells us, Squeeze theorem just tells us that we could grab a function, or we could grab two functions. So if function A does something like this, function B does something like this, and function C does something like this, and they all kind of meet in this area, we could say that if this function converges to this value here, and this function here converges to this value here, then function B should also converge to this value right here. So if they all converge to that value, then they're all, or if the one above converges to the same place as the one below does, then they could all be considered the same convergence sequence. So I know it's a little weird, but let's take a look at these values. So looking at this, I know that, looking at this here, I know that cosine, it kind of just does something like this, where it goes as high as +1, but also as low as -1. So I know that isn't going to change much. If we just set these, like the function lower than this value, if we make it just like a -1/n², that should be less than or equal to, for all values, cosine of n/n². And if we look at the positive version, we know that they go to this right here. So we know that this is going to be true for all values, especially since cosine is either going to be negative, or it's always going to be smaller than everything else. So again, I know that 1/n² is always going to be less than or equal to n² cosine of n. What I meant to say was this value is always going to be bigger because it's going to end up being positive continuously, or maybe not, but it's always going to be bigger than this one over here because this one ends up being negative, which for sure means that 1/n² is always going to be the larger of these two. This one, the numerator being smaller than the numerators over here, is going to make it a smaller value. This one being negative, no matter what, it's either going to be negative, it's either going to be equal to or not equal to. This one here, it being negative, it's always going to be smaller. So we have that. So we'll call this one A sub n, this one's going to be B sub n, this one's going to be C sub n. So starting off with A sub n, so taking the limit as n approaches infinity of A sub n, that's the limit as n approaches infinity of a -1/n², which we've already determined ends up being 0. All right, that's A sub n. Let's take a look at this one over here, B sub n. So the limit as n approaches infinity of B sub n, that's the limit as n approaches infinity of a +1/n². This one also goes to 0. So since those two are equal to each other, so since, based on all this evidence, since the limit as n approaches infinity of A sub n, and this isn't B, this should be C. We're proving B. So A sub n is equal to 0, which is also equal to the limit as n approaches infinity of C sub n. Therefore, we could say that the limit as n approaches infinity of B sub n, this here is equal to 0. Actually, this should be thus, and this should be therefore. B sub n converges to 0. B sub n converges to 0. There we go. If you have any questions, please feel free to ask. Otherwise, bye.